Hello everyone and welcome to another AP Computer Science video. Today's video we're going to move on to an application of arrays and array lists in computer science that are very common, and really it's not necessarily about whether they're arrays specifically or array lists or any collection that a programming language might have, but instead about the idea of how we can use these collections as a very specific tool in a very common thing that has to happen across many different software tools. And this thing is sorting, the sorting or ordering of data in some meaningful way to a human being's advantage. So for example, if we need to sort students by their grades, so we have a list of students that are passing and not passing, then sorting is an important idea. Or sorting things by prices, because we're Amazon and we want to show people the least expensive to most expensive items on our list, or by user rating. Whatever our sorting criteria happen to be, the idea is that the same rules apply. Putting things, data, numbers, strings, values, complex objects in a particular order is an important idea. And so we're going to talk about sorting. We'll do the different types of sorts that we're going to cover both for arrays and array lists, but really the ideas and the differences between them are very trivial. And hopefully by this point we should kind of recognize arrays use the bracket notation for accessing and storing values, and array lists use the get method and maybe the set method or add method or remove method to place items. And so when we do our sorts, the differences between those two things will be very simple. But we'll start off with sorting just numbers. We'll start off with arrays, and then we'll see how it applies with array lists, and then we can maybe move on to complex objects. But the idea behind the sort is essentially the same. What's important to recognize is different types of sorts have different performance trade-offs. So the idea of sorting something for us might be obvious. Look at two things, and whatever's putting from small to big, whatever's the smallest one goes first, and so on. But to do this in an efficient manner, in a consistent manner, maybe the way that we think of the first time around is not the most efficient way of sorting data. There might be really intelligent ways to make this happen, especially for a computer system. So we're going to see different types of sorts. And I'll share with you in the next video some graphs to just kind of prove with real numbers, real sorting tests, the performance comparisons and how some sorts really do a really fantastic job and some don't do a great job, to the point where they're not practical, where they maybe can't sort the data that we need, especially with today's data, often called big data, where there's billions and billions of pieces of information we have to keep track of. Or for Instagram or Facebook or Snapchat, and all this data has to be collected in a way that's easy to manage and search through, then keeping stuff in order is a big deal. So we're going to we'll start on that path of understanding of why sorting is such a challenge, and how it's taken many years to come up with really powerful techniques to make this happen. The first ones we're going to see are not spectacular, but they're also pretty easy to manage, and it would be a good idea to be comfortable with them, not just because they're on the AP exam, but also because they are solutions that do work for limited cases, and they're a good start, and then we can see how improvements really do jump from these basic algorithms. So we're going to go and start off and make a new package in our notes, and I'm going to call this searching and sorting. We're only going to start with sorting for now, but really once we have the sorting done, the searching will become back, and we'll come back to it, and it'll be very useful. So let's go ahead and make a new class, and we'll call this bubble sort example. So we'll talk about that bubble sort, and we'll see a visualization. I'll have a visualization for you in a moment of this sort, and we can kind of see what's happening as we go. So let's go ahead and first make our main, because we're going to eventually test everything that we're doing. What we're going to do is we're going to make a method that accepts an array of numbers and sorts those arrays. Initially the array may be sorted, it may be scrambled, we don't know, we don't care. We'll take the values and we're going to sort them from smallest to big. So we are making some assumptions that they're integer values, and that they're maybe in random order, and we want them from smallest to largest. The fact that it's an array is kind of trivial. The fact that we want them from smallest to biggest is trivial. The comparisons that we end up making can be changed very simply to do from largest to smallest, or from any other organization that we might want. But we're going to start from small to big, and we'll start with this an array of integers. So let's go ahead and start with a small literal array, and then we can know the answer pretty easily. We'll be expected to be sorted, and then we can validate that that works on any array that we give it. So let's go ahead and make an array of integers. We'll call it nums. And we'll give it a literal array, and we'll start off with just some random numbers. So 7, 3, 5, 2, 2, 9, 4, 1, 1, 5, 7. Well, not 7, let's do 13. There it is. So it's not in any particular order. Notice that there's some small numbers in front of big numbers, there's some big numbers, and so on. So the end goal is to make this sorted, and if we saw it, we should see 1, 1, 2, 2, 3, 4, 5, 7, 9, 13. That's the end result that we should get, or yeah, 2 5s. So that's what we should get. It's some sorted list from smallest to largest, or largest to smallest if we decide to go that way. So let's make a method that does this. We're going to do it in a method just because it's easy to call it on multiple lists and validate that this does in fact work. So let's go ahead and say public static. Our sort is going to change the internal values of the array given to it. It's not going to create a new array, though that's something we could consider doing so that we don't touch the original. But in this case, this is kind of an in-place correction. It's going to adjust the internals of the array. So when the method is over, the array has been internally changed so that the values are sorted. Right? This is a decision I'm going to make. We could make a method that does something similar, but doesn't touch the original. But we're gonna touch the original just because that's the decision I've made. So we'll say void is our return type because we're not returning anything. We're just editing the one that's given to us, and we'll call it bubble sort. And we'll see in a moment when we're done and when we visualize it why it's called bubble sort. If you've heard of this, this is great, but if not, you probably would have come up with a solution on your own eventually and then understand why it's called bubble sort. So we'll see that in a little bit. We're given an array of numbers, so I'm going to call ARR just because I don't necessarily care that it is numbers. They could mean anything. They could be temperatures, they could be grades, they could be the number of people in a classroom, in different rooms. It doesn't really matter what the contents are. So the idea behind bubble sort is this. If we look at any two numbers next to each other, it's really easy to decide if they're in sorted order. If our implementation says go from smallest to biggest, and I give you two numbers, one in the first spot and one in the second spot, we simply ask, is the first one smaller than the second one? If so, it's sorted. Otherwise, it's not. So for example, in the pairing 1, 2, this is already sorted. Let me put some comments so this is not visible, right? So that's sorted. In the pairing of 7, 3 is not sorted, right? So if we look at any pairing of numbers, it's easy to tell immediately if they're in sorted orders. If we're going from small to big, the first pairing is sorted already, the second pairing is not. And then the action to sort them if they're not sorted is also very easy. To sort, all we have to do is swap the values. So if I switch the 3 and the 7, that pairing is now in order. And so bubble sort says we're going to look at every pair of numbers next to each other in the collection. So the first two, and then the second and third one, and then the third and the fourth one, and the fourth and the fifth one. So every pairing of numbers with overlap, and we're going to ask, are they sorted? And if they are, we're going to move to the next pair. And if they're not, we're going to sort that pair by simply flipping the values. And then we're going to remember that we had to do the swap, that we had to flip them. And the idea of this sort is we're going to continue to look at every pairing in the entire list until eventually we can get through the entire list without swapping any. So for example, in this array, what we'd say is, okay, look at the 7 and the 3. Are they sorted? No. Then we'll swap the 3 and the 7. And so now this would become 3, 7, 5. And then we're looking at the next pair, and it would be 7, 5. And the answer would be they're not sorted. And then we'd have to switch at the 5 and the 7. So now it would be 3, 5, 7. And then we'd be looking at the 7 and the 2. And then they would not be sorted, and we'd flip them. And basically, we're going to go through every pairing. So these two, these two, these two, and so on. And then when we get to the end of the list, if we made any changes at all, then we have to repeat the whole process. And we're going to constantly repeat and check every pairing again and again. And at some point, we will be able to look at every single pairing. And if no changes made, then we know that the list is finally in sorted order. If we have to make even one swap, that means it's not in order. So try the whole thing again. But if we make it through all numbers, all pairs, and there are no sorted values, there's no swapped values, then we know that we've successfully sorted the list. So this is a repetitive process. The process is going to go through every pair, which is one set of work, and then say, do this looking at every pair until there are no more pairs that have to be switched around. So let's start off with that loop that says go through every pair. And I think this is a pretty easy thing for us to do. We've done it before. We're simply going to go from the beginning of the list to the end of the list. So in this case, it's an array, so dot length. But -1 because we are going to look ahead. So if I'm in position I, we're comparing the ith position with the ith plus 1 position. So for example, if we're at position 0, we're looking at 0 and 1. If we're at position 1, we're looking at 1 and 2. If we're at 2, we're looking at 2 and 3. If we're at 3, we're looking at 3 and 4, and so on. So go from the beginning to the end one early so we don't go out of bounds, but we're still looking at every pair, no numbers missed, because if we're at 13, there is nothing next to it. And then ask the question, are they in sorted order? So if the ith value is strictly less than the ith plus 1 value, and again, I'm saying strictly less than because if they're matched up, then there's no need to swap. Now, we could say equal to, and then we just flip them, but since they're the same value, there's no need to flip them. So we're saying only if they're not in order. Actually, so maybe we should say the opposite of this. Instead of saying if they're in order, say if they're not in order. If this one is strictly bigger than. So if they're equal, then we do no work. And if they're not equal, this one's larger. So if 7 is bigger than 3, or if 5 is bigger than 2, then we need to do the work of swapping. So let's put this in words. Not sorted. Right? So if the current pair is not sorted, so the one that to the left is larger than the one to the right, that's a problem. So we should flip them. Now, to switch two values in two variables or two values in an array, we need a third variable. So let's go ahead and say, and temp is equal to, and it doesn't matter which one we copy. We make a copy of the ith one. We erase the ith one with the ith plus 1 one, and then we equal to the temp. So we've swapped them. So swap these values so they in order. Now this is it for the internal, but this only happens once. There's no guarantee that our swapping fixed everything. It might have actually caused problems. So like for example, these are in order, but if I swap the 5 and the 2, then now suddenly it's broken. The next pair is broken. So this action is not happening once, it's happening continuously. And how do we know it should continue? Is if we make even one swap, then we need to continue. So what we're going to do is we're going to make a variable. Here we go. We're going to make a variable outside here, this Boolean, and say swapped. And what we'll do is every iteration of the outer one, or sorry, of our outer loop, which we don't have yet, we'll say, look, if you haven't swapped, that's great, but as soon as you swap, then we need to let them know and retry it. So at the end of this swap, we're going to say swap is true. Right? So we actually flip them and then let them know, hey, because we screwed up and we had to flip something, we have to recheck the whole list all over again. Right? So we must check the entire list again. Right? Now again, this on its own is not enough, so now we're going to wrap this loop in an outer loop. And the outer loop becomes very simple. We're going to say while swapped is true. And so there it is. And so we're going to say, okay, well, at the beginning of this loop, and now I know this may seem unnecessary because of here, but the next time this happens, if we go through every pair and this becomes true, then we're going to have to, this loop will end, this will be true, and then we'll set it to false and try again. If we manage to go through this without ever setting it back to true, then eventually we're done. And so the goal here is to say, well, while we've made at least one swap, also, in fact, this should be, we're going to assume it's true, and that way this happens at least once. And we're going to try to make this happen. So it says, okay, we swapped at least once, and again, the first time maybe we didn't. So worst case scenario, we're going to look through the list once, and that's okay. We assume it's false. We didn't make any changes. I go through every pair. If we make a change, then we mark it as changed. And then when we get here, if it was a change, we have to do it all over again. Assume that there were no changes. Go through every pair. If you make a change, mark it. If we manage to get to the end of this second loop, where the swapped is false, that would imply that we've made it through the inner loop without ever making any changes, which would imply that every pairing is in order, which implies the entire list is in order. And there it is. So that's our method, right? So bubble sort says, look, while you've made changes, go through every pair and swap any unsorted pairs, and then try again if you make any changes. And eventually you will not swap anything, and then the loop will be over, right? And so that's the idea here. And so let's test if this works. And if we did it correctly, then we can visualize it, and then we can see how this goes. So let's test this out. I hate that this formatted for me, but that's okay. So let's go ahead and print out. So let's do a simple for loop, enhanced for loop. And we'll just print out, I don't really care about what it looks like. We'll say num_zi plus space. There it is. Not num_zi, sorry. What am I doing? I'm saying n. So we're going to print out each value. We're going to sort it. So we're going to see the original list unsorted. We're going to call our bubble sort on that same list, and then we're going to reprint the same list, and we should see them in order. So let's see if this works. So this is our sort, and let's test this out. It'll take a moment to compile, and hopefully we see results. Oh, I should definitely put a println after each one. It's very important, otherwise they all end up one giant line, and we can't see it. So there it is. Here's the original unsorted, and notice the new sorted list. And there it is, 1, 1, 2, 2, 3, 4, 5, 5, 7, 9, 13. And now this works for any list. Now, of course, the problem becomes, so I'm going to make a new set of numbers. Let's do 8, 8, 4, 13, 13, 19, 4, 2, 1, 7, 5, 6, 21, 14, 31, 29, 11. So there it is, and if I run it again, notice this is not in order. It should still work. And there it is. There's the original, there's the sorted version. So it handles duplicates, and it sorts them all, right? So I hope you see this idea of what's happening. Is we're constantly swapping through, and this seems fast, but if I made a bigger array, so I'm not going to put a literal, but if I made a method that generates an array of random numbers and I make it really large, it's going to decay in performance. And I'll show you soon in another video a graph of how bad this is. Unfortunately, bubble sort, even though it is a solution, it is a pretty poor solution in reality, and once we hit a couple thousand values, it starts to really slow down. Right? It seems instantaneous, but I could make maybe 1,000 values, and you might notice in time. And you might say, well, what's half a second? That's so fast. Who cares? But in the real world, we all know from experience, if Google takes more than half a second to find your results, some people get agitated. Right? We expect very fast performance for things. And something as easy as, and I say easy with quotes, right? Air quotes, something as easy as putting numbers in order, you would expect to be extremely efficient. But the reality is bubble sort is not really that great. And we'll come up with some other solutions that are maybe better. And there's a lot of research in many, many years of computer science studying by a lot of different people to find much better solutions. And there is no perfect solution. However, bubble sort is a solution that I think beginners can understand and be comfortable with. So I'm going to open up my visualization, and we'll see what bubble sort looks like, and we can see maybe why it's called bubble sort. Okay, so here's the visualization we're going to have. In this picture, each bar represents some random number, and you can see that if I pause this little program, we can see this is comparing 13 versus 51. So when the two bars are blue, that's the current pair we're looking at. When it turns red, that means they're out of order and it needs to flip them, and you'll see it's changed. If it turns green, then they're already in order and it can move on to the next pair. So I'm going to go ahead and play it, and we'll watch it for a little bit, and we'll see how this happens. So the first pair is good. Notice how if it turns red, it's flipping them. If they're green, they're now in order. And so if you pay attention, you'll notice that what is happening is that the largest bar is bubbling to the right. And so then there it was. If you see any red, that means there was a change, and therefore the whole list must be rechecked. And you'll notice that every time we go through, there's a correction of a large versus a small. And so the further into the sort that we have, the less and less work is being done. But every single time there is a swap, we must go through the entire list once more. So notice that so far it seems like a lot of them are in order, but sometimes when we fix an order for one pair, we break another pair. But you can notice the right side is slowly being corrected, and the bigger bars are bubbling to the right. Or you could say the smaller values are bubbling to the left. Now again, there are other different implementations of bubble sort, but this is the simplest, most naive version. And though it does work, it can be slow. This is obviously slowed down on purpose. If we let the program run kind of on its own pace, then it'll be as fast as possible. This is a visualization that slowed it down for us to see. But you'll notice that a lot of pairs are good, but as soon as a pair has to be corrected, we must try again. So let's keep watching, and we'll notice that obviously less work happens as we go to the right because more and more pairs are bubbling. Right? So notice that those pairs all lined up and there's no problems. Right? So we correct, we correct, we correct, and these are all good pairs. So we're almost there. I still see probably at least a good number of swaps still happening. At least 3 more swaps. Or 3 more bubbles up. There you go. Now the next one will bubble up, which is the biggest bar. And we'll see. We're almost there, but notice there's a lot of time wasted. You can see that once we're past the pairs that are broken, we have to constantly recheck pairs that are not necessary. Now, maybe implementations could go through and mark the last place that was corrected or the last bubble that was marked, but those are work that we don't necessarily. There it is. Now, I think one last check will go through every pair, and there will be no changes, and then the sort will stop. And there it is. So hopefully we can see why it's called bubble sort. It is not a great solution. This is only on about 20 numbers, and it's slowed down. But we would see this motion, and I'll give us a better visualization with more numbers quickly, and we'll see what this looks like. So here's one last visualization without the colors, just so we can watch it quickly. And this is sped up a bit, but we can still see that this is a slow implementation. You do notice the bubbling of the largest bar does eventually flow to the right in this picture. This is only about 50 numbers. So again, and this is only each comparison is really, really quick, but still, even if we didn't draw it on screen, it would slow down pretty quickly. I mean, 50 numbers is very slow, but the idea is that there's a lot of work, a lot of effort being wasted. So this is an implementation, but not a perfect implementation. So in our next video, we will see a slightly better implementation of a sort. It's not spectacular, but it's an improvement on bubble sort, and we'll go from there. And then we'll do a third sort, and then we'll talk about just overall efficiency. Later on in the semester, we will do one last sort that's much, much better, much more stable, and more common today. And we'll talk about searching as well, because sorting and searching are very much tied together. So in our next video, we'll talk about more sorts. I'll see you in the next video.